Hello. Today I want to present a topic on signalized intersection. So let's start. So the topic of my presentation is uh, benchmarking intelligent traffic signal control strategies on a small Sumo network. I use TracI. I am Shoro Borua presenting the topic. And actually, I try to use the reinforcement learning, especially the proximal policy optimization method to optimize or use the adaptive signal in a 2x2 grid. However, I also use model predictive control and the max pressure control system as well in the signalized intersection. So first, let's start with the overview. If we look at here, we can see that firstly, I use Sumo simulation using TracI as a test bed, and my traffic demand is uniform light traffic demand, and arrival rate for each origin node varies from 50 to 150 vehicle per hour, and OD pair, no OD pair has not more than 50 vehicles. Even whatever OD I assign, those are 50 vehicles per hour. I'll show the network a little bit later. And for performance evaluation of signalized control, I use fixed time, actuated signal, max pressure, Kalman filtering based model predictive control, Kalman filtering based max pressure method, and lastly a hybrid technique I try to formulate and implement, that is model predictive control, convolutional network, and proximal policy optimization technique I like to use here. In the next slide, we can see that the why model predictive control, graph neural network, and proximal policy optimization type reinforcement learning I used here, because each of the three component has three separate rule. If we look at the graph convolutional network, it learns from special traffic features, and I set up E2 detector, that E2 detector in the network, and from the E2 detector, the graph convolutional neural network will learn special information related traffic. Then I use model predictive control because it can evaluate short-term traffic prediction and compute near optimal signal timing for short-term basis under specific constraint. So model predictive control is a good option in this point of view. Next comes the PPO based reinforcement learning. It learns long-time adaptive policy, since the model predictive control use work under constraint and short-term evaluation, but PPO works on long-term adaptive policy and improves the result over repeated simulation. So I combine all these three and create a hybrid reinforcement learning technique. Now let's look at the model. Here is the 2x2 road network. There is total 4 signalized intersection, and I have total 4, 4, 8, 9, 10, 11, 12 nodes. And in the right side, you can see that the closed lookup where the detectors are located for one in every approach in every approach direction. For every lane, we can see that the three sets of detectors are used. Firstly, I use the stop line detectors, which are located just upstream location, and the length of the detector is 10 meter. To mention here that I use E2 detector, that is video camera, for all over, and an advanced detector that is located 200 meter upstream and length of it is 20 meter. Lastly, the Q detector, I named it a Q detector, which is located 400 meter upstream and it is 30 meter length, and each approach of this network is 3 lane and length is 500 meter. This is all about the model description, and I have already mentioned that the demand of my traffic is 50 vehicle per hour for each origin destination pair. Let's look at the challenge. What is the main challenge of PPO implication? It has, I come up to 4 points here. Firstly, it takes long training time. From my experience, it takes almost 4 to 5 hours for this type of a small network for completing 200,000 time steps, and computation is expensive, lot of time consuming, especially for home PC. My PC is Core i5 without GPU, and RAM is 16 GB. So it's not actually enough for this small, even for a small size of model to model PPO good. It's a challenge here. And hardware limitation, because training PPO that I mentioned previously, it takes substantial computational resources, high performance CPU, GPU required, limited hardware restriction makes complexity and prolonged training time. And realistic simulation modeling, whenever we develop simulation model accurately with try to match up with real world traffic, it becomes challenging, because field data, we have to calibrate a lot of things with the field data. Firstly, the traffic demand, vehicle behavior, signal timing, network characteristics, all this we have to match with simulation, with a field, along with the simulation. So training proximal policy optimization to the real world scenario can be a little bit difficult. And then comes the scalability. Then most PPO actually modeled for small traffic networks. However, for large scale urban network, how to implement the PPO and the hybrid policy, it remains lot of challenging, because state and action, two important thing for reinforcement learning, rapidly grows, and computational complexity increases exponentially, and training become very difficult. So these are the four main challenges that hinders to use hybrid PPO in models. If we look at the results, I am discussing about the results first. We can see that since we have used total 6 controller, signalized type controller, and there are, here I am presenting 4 parameters: average delay, average queue, total throughput, and average speed. That max pressure control actually better for average delay, queue, throughput, and average speed. There is no doubt. But if we look at the hybrid, our hybrid model, that is MPC, model predictive control, graph convolutional network, and proximal policy optimization, it's little bit worse, but not that much poor. But if we look at the actuated and the fixed time, they are not working well. Now look at the travel time comparison, fuel consumption, and carbon dioxide emission comparison. Similarly, max pressure control beats a lot, and the max pressure control with Kalman filtering, model predictive control, and the model predictive control, and the model predictive control with Kalman filtering, and our hybrid model, they are also a little bit somehow competitive. However, the fixed time and actuated does not play well here. We can see that the queue length heat map, actuated is almost a lot of queues. Fixed time has some queues. However, obviously the max pressure control has almost no queue, but max pressure control with graph convolutional network and PPO, the hybrid model has little bit somehow small size of queue. We can see over the time bucket here. And if we look at the controller computational time, obviously our hybrid model takes a lot of time, which makes it little bit challenges. It's actually after training. Whenever we test, it takes 34.83 seconds for average decision making, whereas max pressure control takes only 2.58 second microsecond for every decision. Obviously, max pressure control overcome or defeat all other methods. There is no doubt, because our network is actually small, and our hybrid model cannot actually properly train. That's why it cannot beat the max pressure control. Now look at the comments for every five controller against the baseline. Obviously, max pressure control is the best performing for all traffic efficiency, mobility, and environmental metrics. And obviously, it has main advantage, that is low computational cost. Actuated control is the worst, and because it is insufficient for coordination control. Kalman filtering with max pressure is somehow better, but not like max pressure control, because Kalman filtering is not actually needed for Sumo based simulation, because Kalman filtering works for the smoothing. In the simulation data, we have all detectors data from the detector, so KF actually do not needed. Kalman filtering with model predictive controller, it also works not bad, and our hybrid model is not also bad, but it raise a question, the justification of substantial higher computational complexity, because our simulated network is 2 by 2, and additional learning capacity of the graph convolutional network and PPO framework is not fully utilized. That's make a question about using the complex time consuming hybrid models. That makes a question. And if we go through the details about in the comment section regarding why our hybrid model is not performing, because I identified 7 points actually. Firstly, undertrained. The PPO policy is undertrained. Though I have used almost 200,000 time steps, but each step is full of 10-second decision back, is not enough for PPO to learn good multi-intersection coordination. I'm not sure about that though. Policy has not covered. It's making decision closer to random or partially learned than a refined strategy. That's the point. And if we look at the action space, the second point, the action space gives people very little leverage, because action space is very little, because there are first 4 action, 0 is keep, 1 is extend, 2 is shorten, and nothing happen when max green is provided. Action 3 is the switch adopt the model predictive control phase. So PPO has little space to work, because MPC, that is model predictive control, propose, then PPO works on it. So fine gate timing control is not possible here, and its output is capped by the model predictive control. That's a problem, because PPO can decide only when it accepts, because firstly what model predictive control. So for controller 4, say the Kalman filtering model predictive control itself reach 0.8 delay. So controller 6, that is our hybrid model, MPC, GC, and PPO, never beat that result. So it has 1.29 second average delay. In the 4th and 5th, if we will look at the points, the GCN embedding untrained, and effectively random noise it creates is random weights and never gets trained jointly with PPO. There is 8-dimensional embedding and no learning traffic prediction signal. It just adds extra uninformative dimension. So PPO has to learn, ignore, and make learning harder than easier. It makes learning harder. So GCN, that is graph convolutional network embedding, is almost remain untrained, and random noise it creates. And reward signal is coarse and sparse, and our reward is computed only once 10-second division block, and the reward equation is throughput into 0.1 minus halting into 0.3 minus waiting into 0.05. It not shaped every second, and combined 4 intersection. We already said that it is 2x2 signalized intersection and sharing one policy, credit assigned, and intersection decision caused by reward, and it is ambiguous, slowing the learning further. It not actually provide the much better result. And if we look at the 6 and 7 points, one shared policy across all 4 intersection, it limit expressively, because a single multi-discrete output, different intersection has different traffic pattern rather than spatialing, and it underperformed the path junction aware policy. Okay, it underperformed path junction aware policy is the main topic, because I am sharing one policy to 4 intersections, and higher computational cost, lower payoff. It takes almost 34.83 microsecond for average decision making in the controller 6, our hybrid model, but its performance is not that better, and so it lands in the 4th place. So what is the bottom line of MPC, GCN, and PPO controller is that it is under-trained refined layer sitting on top of MPC engine. Low impact action space, randomly initialized GCN. So this small 2x2 network lands close to MPC backbone rather than surpassing pressure controller. That's showing that because it's land over the MPC, so it cannot beat the MPC, that model predictive control. That's the problem. And GCN is not working properly, not properly trained, it is randomly initialized. So overall, that method is not that bad, but it's not best. It's obviously competitive, but it's not that best. That's the problem. Here we can see in the code explanation the total framework. We have actually 4 layers. First layer is input and configuration. Second layer is run initialization, then controller execution loop, and lastly output generation. If we look at the first layer, the configuration, we have all paths, Sumo setting, MPC horizons, Kalman noise, parameters, GCN and PPO size, assigning all this stuff, and data files. We have network demand file, detector location file, Sumo CFG file, and also relative path are assigned fixed. Then run initialization, we have almost 5 components. Firstly, the process run simulation, utils and sumo _util.py that learns the TracI, then network discovery or network graph, auto discover the traffic lights, phase and neighbor topography is the part of the GCN. Then approach classification, it classifies the approach into 4 approaches: north, south, east, west, and bucket incoming edges geometrically. Detector, it detects the detectors from lane to detector, traffic light to approach, and detector list mapping for optimization. Phase pre-computation, it compute green approaches and green phase indices. In the 3rd layer, it is the largest layer, controller execution, drives the main.py in the simulation loop. It do that, and 6 controller using same seed and simulation duration, that is 3600, and it utilizes the utils or matrix pi, collects step data, and also within the step data it collects vehicle speed, waiting time, queue counts, and emission, that is fuel, carbon dioxide, and other gas emission, throughput, and decision times is collects, and stores time series, and all summarize in the dictionary. And all controllers firstly use the base control, track phase, time, and decide traffic light and simulation time. Then in the next phase, if we look at that, almost we have the regarding except the base controller. Along with the base controller, we have 5 controller. One is fixed time, that is used as baseline, then actuated control, then max pressure control. If we look at the actuated control, it use the gap out logic, that is use the sum of green time by max green time and differ sumo yellow. It extend green and early end if gap threshold. So it use the gap out logic for actuated controller. For max pressure control, it computes upstream Q minus downstream Q and switches to highest pressure phase and catch detector and halts. For Kalman filtering or with the model predictive controller, we can see that it fills Kalman filter, then Q by arrival, estimate, resolve for every 10-second step. Model predictive control update interval and reuse the solution. For max pressure controller, it uses max pressure controller with Kalman filtering, replaces raw Qs with Kalman smooth estimates, and it's little bit provide robustness, but this is a small network, so actually, and also I use the simulation. So Kalman filtering with max pressure control do not actually give that much benefit over the max pressure control, rather than it takes a little bit more simulation time. If in the controller 6, which is our main focus or target, that is PPO, GCN, MPC, firstly, it generates GCN model.py. It is light GCN 2-layer embedded intersection features. Then use Kalman filtering and filter 1D smooth Q and occupancy and approach Kalman estimator. Then PPO environment, it use GIM library and one-time training, wraps the environment with monitor, training, PPO, CPU force, multi-layer perceptron policy, and save the model and wrap time training. And lastly, the combined hybrid model, MPC, GCN, PPO, it runs Kalman, GCN, MPC to get the candidate phase, then use PPO policy to decide switch or stay. And it feed into controller like controller 4. And all this output are stored into plotting.py using graphs of 13 categories of 300 DPI, matplotlib figures, time series comparison heat map and PPO curves, and in the recorded result in the Excel output, and we can see the summary data in the Excel sheet. And this is all about the overall coding of my benchmark framework. Let's deep dive into individual works. If we look at our main focus of hybrid model, MPC, GC, and PCO, we can see that the firstly current signal state, it yellow signal return. If non-yellow signal, then input processing, raw data detector, it collects Q and occupancy using filter, Kalman filter, smooth Q and arrival estimates, then counter and check MPC, model predictive control step counter. I'm stopping over the above side. In the below, it creates build focal local features, Q, occupancy, count, speed, waiting time for current intersection, and then MPC search using controller 4 and MPC candidate phase, and green time is assigned, and PPO model is loaded. If yes, then it use light DCN and 8-dimension embedding, concatenate 4 approaches, 5 row features, 4 approaches to Kalman estimate, and 8 DCN embedding, and current phase is identified. And in the above, the purple color, assemble full observation vector PPO policy, then model predict deterministic. If it is determined true, then comes to decision logic. In the above part, we can see that the PPO model loaded. If no, full back mode, switch to MPC phase and terminate. But in the below, in the right below, we can see the PPO policy feed into the logic, decision logic. Action for this intersection. Action 3, switch, apply MPC proposed phase. Action 0, 1, 2, 3, 0, 1, 2. 0 is for keep, 1 is for extend, and 2 is for shorten. 3 is for actually the switch. Then stay current phase unless elapsed max green. Current phase, force switch to MPC phase, or stay in the current phase is the way the logic works. So it actually use same as controller 4. If you look at the what is our controller 4, our controller 4 is Kalman filtering with model predictive control. So our PPO is actually PPO, the GCN and PPO works over it, over this model actually. If we look at the most efficient model here, the controller 3, that is max pressure algorithm, we can see that the firstly, if current signal state is yellow, if it is yellow, then return, let clear of it, or if it is no, then elapse, it is minimum green, then return green floor and force. If it is no, then elapse max green and decision interval. If it is max green, then return. If it is no, then update last decision to no. And this update is aggregate approach detector state, update Q per north, south, east, west bound, and estimate downstream Q, average halting of vehicle over ongoing lanes. For every gain serving phase index, it calculates the pressure that is in the denominator. In the numerator, in the above, the sum of upstream Q of average approach minus downstream approach into number of approach served. So calculating the pressure, pick the phase of highest pressure. If it is no, it backs to the aggregate current approach detector state. Or if it is yes, then switch phase, reset the time. Now look at the controller 4, that is Kalman filtering using the model predictive control. It starts step first, then check yellow signal state. If yes, then return. If it is not yellow, then proceed in the two-way. Firstly, the aggregate the approach detector data, raw counts, and apply Kalman filtering, shorten, smooth the Q and arrival rate. Then all these meet up to increment MPC step counter. Is elapse is less than minimum green? No. Then proceed. If it is yes, then go back as return. If it is no, then determine MPC resolve time. Is counter equal to updated interval or max green? If it is max green, neither return, either proceed and set up, reset the step counter to 0 and call lightweight MPC solver, and lightweight MPC logic works with iterate the feasible pairs is phase and green duration, simulate 5-step horizon Q evolution, and within that 3-step control and hold green. Calculate total cost Q. Total cost is the Q, delay plus stop and peak, phase and green, lowest cost, and it feed up to the cache and execute choice. Output phase and green duration is chosen phase, current phase. If it is no, then done. If it is yes, switch phase, and this is the end of the step. And this is all about the, I'm not talking about the Kalman filtering based max pressure control, because it is almost similar, just feeding up with the max pressure control with Kalman filtering, and also not talking about the our actuated approach and fixed time. Fixed time is 42 seconds for each approach and 3-second green, total 4 phase it is used. So an actuated is gap out logic, and as I told about the Kalman filtering with max pressure control, it just max pressure control, just filtering, just smoothing with Kalman filtering. That's all about. And this is the GitHub repository of my task, and I am discussing all of the matter here. So thank you so much and watching this video.